Welcome back, everyone. So we're going to pick up where we left off last time. But actually, I'll start with a brief recap. So we had small, idempotent, complete, stable infinity categories. We've put this inside as a full subcategory of a bigger category, which was this PR stable dualizable stable infinity categories. And we had the result that every localizing invariant, so extends uniquely to this world, to a localizing invariant. And we saw, I think, one class of examples of dualizable stable infinity categories, namely sheaves on compact Hausdorff spaces. So for the first half of the talk, what I want to do is give a bunch more examples. So objects C in PR ST dual. And the general framework in which I'll discuss them is kind of maybe convenient for writing things down off the bat, but it's not necessarily the most convenient way to understand the categories. But just as a first pass, I'll start with this. So a general source is idempotent algebras, or idempotent maps of algebras. So if you have A and B, and this is a map of rings, and let's say just unital associative, and maybe ring spectra are also allowed. All right, let me say in principle allowed, but in the examples I'll discuss, A and B will actually just be ordinary rings. But in principle, ring spectra are allowed. Well, okay, well, when you have a map of rings, I have to make some convention about whether I'm doing left modules or right modules, right? But let me just, don't bug me about it, please. Unless you see an honest mathematical issue. So DA stands for, I don't know, left modules? Well, you certainly get an induced functor here like this. And the situation we'll be interested in is when this is a localization functor. So AB is called idempotent if this functor is a localization.
So this continuity just the previous one. Yeah. Like last time, so you define this one, and this could be represented as limits, like in the usual continuity terms.
No, this was the way you prove this theorem, that there's a unique extension, is you give a formula for this, and I'll just recall the formula. This was defined to be, you take your E, you apply the Kalkin construction to C, and you take compact objects there, and then you hit that with E, and then you take a loops.
Yeah, no, but I mean, this can be like written as limit over E of something else.
Well, limit, I mean, but if by limit you mean loops.
If limit makes sense.
If by limit you mean loops, then yes.
Are you asking if it's a right hand extension?
No, I mean just the word continuity here.
Oh, why did he call it continuous? I don't know, but
He reminds some like limit.
Well, I don't know. Well, just a sec. I think these things were, in the one categorical setting, these things were called continuous categories already. And we'll see some aspects of this sort of continuous behavior of these non-compactly generated examples. It was a felicitous choice that he called this continuous K-theory, because it will actually match a previous definition of continuous K-theory. According to Sasha, he didn't have this in mind at all when he made the choice of notation, but then he proved it is true. So we'll discuss that later today. very felicitous, yeah.
So the definition is always this formula for E continuous.
That is always the formula which proves the existence and uniqueness claim of this extension, yeah. You could say it's the definition if you want, and I guess you'd be right. I prefer to think of it as it's the way you prove a theorem saying that there's a unique extension, yeah. But it works for any localizing invariant. It doesn't have to be K-theory. And in fact, that's what I explained in the first lecture.
So it means that in C0 of E of that is always 0.
Oh yeah, if you take the end of C and you take an E theory of that, E of that, you always get 0. Eilenberg-Swindle works for any localizing invariant.
Oh, okay.
Yeah. Okay. So in this case, we get a dualizable category. I guess I could call it dA to B, or I don't know, dAI, if I is the kernel of A going to B. If A going to B happens to be a surjection, I don't know. Yeah, if it's a surjection of ordinary rings, then but it's just defined to be the kernel of this localization functor. So so it's a way of presenting a dualizable category by just a map of rings. And I'll make very quickly a remark, which Efimov has explained, is that actually every C in PR ST dual is of this form. But presenting it like this is not necessarily the most convenient way of understanding the category, so I don't think this is an important remark, but it's maybe nice to know.
Are A and B known in the case of nuke of some analytic space?
Your question is not well defined. Because A and B are not uniquely, you mean do there exist?
Yeah, I mean, this one
yes,
you say
there exists.
But yeah, are there some A and B known?
One can write down A's and B's. His proof shows you how. I mean, if you can ask if there's a particularly nice choice of A and B, then the question's getting better and better, but less and less precise. So I mean, that's what I'm trying to say with my remark. Yeah.
Yeah.
It is of this form for classical rings or for ring spectra?
Ring spectra, yeah. So I have to allow ring spectra. And so, more concretely, what does it mean that this is a localization? It means that the right adjoint is fully faithful. So, well, it's very simple to check. This is just a tensor product condition. So say, yeah. But now let me emphasize that even if A and B are ordinary rings, we have to understand a derived tensor product here. So this is why it's called idempotent. It's because if you tensor B with itself, you get B back again. B is an idempotent in A algebras. And this is kind of, I guess, you apply to, yeah, so you think of this as a tensor AB, say. Now it depends on whether I'm thinking of left or right, I guess, I don't know. Yeah.
So the map, it should be inverse to the multiplication map, so all the maps, all the conditions should be equivalent.
Maybe.
And in particular, idempotent in the sense of left module should be the same as in the sense of right module.
Yeah, you're right. Yeah, thanks, you're right. Yeah, thank you. Of course, yeah, it's true. Yeah. So what Ofer was saying is it's the same thing as asking the multiplication map to be an isomorphism. So it doesn't matter whether you use left or right. Thank you. I'd forgotten that, yeah. Okay. Okay, so let me make a further remark. So there's a theorem, I guess. So there is a temptation to pass to the ideal in situations like this, and indeed it turns out, at least almost always, that this category here, this fiber, is actually just an invariant of the non-unital ring you get by taking the kernel, the ideal that you have there. And I guess this kind of phenomenon was investigated by Wozicki, and in the present context by Tame. And so for a non-unital ring, ring spectrum, let's call it I, because we're going to be thinking of it as arising from as an ideal in a unital ring. The following are equivalent. So one is kind of that. So I is what's called H unital, or sometimes people call it Tor unital. And it's a non-unital ring, but the best approximation to unitality that you can demand in such a situation is that you have the following idempotents. And this does make sense, even without a unit. This is a semi-simplicial realization. But it still makes sense, and in the unital case, it is the usual thing. And you can, if I is a discrete ring, not a spectrum, then you can write out the two-sided bar complex or whatever. The second condition is that, well, you can always adjoin a unit to I, and I guess I'm working over the sphere, so I adjoin this, add a unit, but I call it a copy of the sphere. And that has that you can then kill off I, and this is a canonical way of putting any non-unital ring inside a unital ring. It's called the unitalization. And this is a the other condition is that this is a localization, or an idempotent, I should say, sorry.
And if you work over HZ, is it the same as using it instead of S?
Yes. For certain, if I is connective.
In Suslin, in Wodnicki and so on, they did usual homological algebra.
Yes. For an ordinary ring, it's definitely, if I is connective, it's definitely true. So I was gonna ask Georg about this actually. Let me keep going. And the third condition is that whenever we have I goes to A goes to B, and these are rings or unital, and this is a fiber sequence. So I is an ideal given as the kernel of some map of rings, then A to B is idempotent. So if you know it in the universal case, or then in fact anytime you see that same ideal as a kernel, that thing has to be an idempotent situation. And then there's a remark. So I think this was Tame, well I guess probably also Wodnicki in the classical case. Suppose A to B is idempotent with A and B connective. Then I equals the kernel or the fiber is H unital. So it's a kind of converse to 1 and 2 implies 3. Or if you just have it for a specific example, then automatically, it doesn't have to be the universal example, but any example, then it'll automatically hold for any example. So Georg, is the connectivity hypothesis necessary here?
I don't know.
Yeah.
It's a long time ago, but I don't remember. I think I don't have a counterexample, but I also couldn't prove it.
Right. Okay. That makes 2 of us. So that's an interesting question. Let me raise it as an official question. Is connectivity necessary here? In this remark.
So if you have a localization of a usual commutative ring, let us say this is an idempotent in your sense, yes?
Yes.
And the kernel is a non-connected.
Yeah.
And it is H unital.
Yeah.
Okay.
I mean, I think I'm remembering correctly that the connectivity hypothesis was on the rings themselves and not on the ideal. Yeah, I mean the proof, yeah. Okay. Okay, so that was a bit of just a framework for thinking about this. I'm not sure I'll actually use any of this, but just it might be nice to keep in mind that it's, yeah. I mean, we're doing something better than passing to the ideal. We're passing to the category, which is the fiber, and that is a nicer thing to consider, but it might just be nice to keep this in mind. Okay, so what are some examples? So let me start with a boring case. So let's say that A is a commutative Noetherian ring.
Sorry, so did you say that the fiber has some description purely in terms of I, or is the fiber on the categorical?
Oh yes. Oh yeah, this is also independent of the presentation. That's a Thomas excision theorem, or it also follows from follows from the properties of this thing here. Yeah, the category also it will be the same as the category you get in the universal case. You just write down some localizations. I mean, yeah, you have a pullback square and you're looking at the fibers. Pullback square of categories and you're looking at the fibers. They're the same. Yeah.
To make sure, like in this theorem, you do not assume I to be connected.
That's correct.
Okay, but in this remark.
Yes, in this remark, there's some connectivity hypothesis, which I'm curious about whether it's necessary. Okay, if A is commutative Noetherian, then every idempotent A going to B is of the form B equals A S inverse for some multiplicative subset. So every, in the commutative Noetherian case, every idempotent is just a localization. And well, this is boring because in this case, as Georg already explained, so D of A to B is already just compactly generated by, I guess, the fibers of the elements in S.
So in commutative algebra, one knows that in the Noetherian case, you can have affine open sets in spec A, which are not principal.
Oh, you're right. Ah, darn it. Yeah. Oh, darn it. Yeah, I mean, you're right. I said this wrong. Yeah. You're right. Shoot. Let's say connective. Well, yeah.
So it should be of the form that spec B to spec A looks like though it's a injective isomorphism on local rings, some induced topology, and all of this. So it is kind of a more constructible.
Yeah, is glued from those of the form. Thank you very much. I was being a little too sloppy. Yeah. Oh, glued from. Yeah. Glued from those of the form. Finitely glued. Yeah. 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 Thank you very much, and my apologies for the incorrect statement. Yes. Okay. Okay, but anyway, in any case, it is compactly generated. So that's boring. But it turns out that once you move beyond the Noetherian setting, then you get a huge amount of examples. So less boring. So if we have A going to B, and it's a surjective map, and these are perfect FP algebras, then it is idempotent. And this uses Gaber's observation that there are no higher tors in perfect FP algebras. You can think perfection kind of clearly kills nilpotence, but it also kills higher nilpotence, as you can check by looking at the universal case of adjoining a generator in positive degree and just calculating the perfection. You'll find it disappears. So that means that if you form the derived push out of B over B with A, which is some animated commutative ring, it can't have any higher homotopy because of the perfection. And then it must be concentrated in degree 0, so we only have to check an underived thing, and then that's clear from the surjectivity. Okay. So you get some category, you get some K-theory. I don't know what to do with it exactly, so I won't discuss it too much. There's a variant. So this also works if A is integral perfectoid and B is perfect still. Okay, and so that's the famous situation of almost mathematics. So the main example would be A is the ring of integers in CP, and B is the ring of integers in CP modulo the maximal ideal, which is, if you've never seen this before, very different from modding out by P. You're killing a lot more. You're killing roots of P as well, for example. Yeah, so that's all.
If you have a perfectoid ring and you take any radical ideal in the tilt, and then you, using this element, you generate an ideal in the perfectoid ring, then this has the same property.
Okay.
I think only P completely, right?
Yeah, P completely. Well, okay, but I made my target be FP. Yeah. No, I don't know.
No, I proved it. So this is my paper with Romero. I mean, it is too abstractly. So since it looks strange at first because they are not complete, but still it's true I mean, in the
okay.
It's as far as I remember, but maybe I get it wrong.
Extension of this. Yes. So where B is not necessarily. But I'll explain. So yeah, if B was not perfect, but another integral perfectoid, then in general, it would only be true with P-completed tensor product. We'll see later a way to accommodate that anyway.
Yeah, but I do something where the quotient is not complete, but it holds on the nose.
Yeah, okay. The quotient is not complete in that case. Interesting. Okay, yeah. All right. So that. I'll say you can also, once we talk about rigid categories and the possibility of using those as base categories for the whole story, then you'll see how you can even accommodate situations where it's just only a P-completed tensor product. That it's only idempotent in the sense of P-completed tensor product. You'll see how you can also get dualizable categories out of that situation. Okay, so those were some kind of, rather non-Noetherian kind of arithmetic examples. But more classically, in the original work of Wodzicki, he was interested in examples coming from functional analysis. So let me make a little discussion of that now. So there's a theorem of Wodzicki. So if A is any, say, unital C-star algebra, and I is a closed, norm-closed, two-sided ideal, then, well, I could say I is H unital, or I could say that A going to A mod I is a idempotent.
Do you take ideal in the C-star sense, or star ideal?
Yeah, star ideal, thank you, yeah. So I want the quotient to be a C-star algebra, yeah. I wonder if it's actually necessary for the result. I think it might not be, but let me be safe. Okay, so I want to give the proof just so you have an idea about how you could ever possibly verify such a thing. You have to calculate higher tors between functional analytic rings. It sounds a bit daunting. So I want to explain the mechanism by which this kind of theorem happens, but I'll explain it just in an example. So example will be, I'll choose a commutative example. I assume that's going to be easier to understand for most of us. So let's take continuous functions on a compact Hausdorff space. And let's say I is the, then we choose a closed subset Z, and then let I be the set of functions vanishing on that closed subset. So what's the mechanism by which this kind of result happens? Well, here's a first remark, is that this idempotency, B tensor A, B isomorphic to B, is equivalent to, idempotency of B is actually equivalent to, if you chase through cofiber sequences, it's equivalent to idempotency of I, sorry. And this implies surjectivity on pi naught, which is the statement that the ideal is its own square. So that's the very first most basic thing you'd need to check, is that every function like this is the square of another function satisfying the same property. But you have to do a bit more because you also have to control higher tors in the self-tensor product. What?
What is B here?
A mod I. Yeah. Oh, it's also continuous functions on Z, by the way. Yeah. That's not exactly obvious, but okay. Yeah. Right. Okay, so what's the mechanism by which this happens? So I claim that what happens in this case, and actually happens surprisingly often in functional analysis, is that this ideal is flat, but for a very specific reason. So the claim is I is a filtered colimit of free modules, or A modules, sorry, of rank 1. Flat as a, let's say it's flat as both a left and a right A module, and now yeah. So to check idempotency, it would be enough to check it on pi 0 and then to prove that I is either flat as a left or a right A module. And then, so the flatness is the key claim, together with the idempotency I equals I squared in the classical sense. So yeah, the claim is just that it's a filtered colimit of free modules of rank 1. Well, what does one need to prove to show this? Well, first you should show that every finitely generated ideal is contained in an ideal generated by a single element, and then you have to do a bit more. If f1.fn are in I, then you can write each fi as fi divided by the maximum of the absolute values, the square roots of the absolute values of the fi's, multiplied by the maximum of the square roots of the absolute values of the fi's. And if we call this expression equal to g, then you've shown that every ideal is, every finitely generated submodule is contained in a one that's generated by one element, namely this g here. And then you have to do a bit more. Then you can do the same for g. Then you can also write g as g over over square root of absolute value of g times square root of absolute value of g. And here you can see that if the map multiplication by g had a kernel, then you factored it in a way that this one has the same kernel. And then that's the extra thing you need to check to see that it's really a filtered colimit of free modules and not just a filtered colimit of one mono-generated modules. So there's some business, you have to control the kernels a bit, but the basic idea is you can do expressions like this. And the same argument, this same kind of factorization proves for you that I equals I squared. In fact, it proves that every element in I is a product of two elements in I. Okay?
Is this still true in non-commutative setting?
Yeah. Yeah. This is true there. Yeah, I wish he had phrased it like that. Then I would have understood it 5 years ago instead of while I was preparing these lectures.
Okay, so you use some kind of polar decomposition of operators to reduce to self-adjoint positive, and then you can, of course they don't commute, so you cannot do the same thing, but you can still try to do, they have canonical square root, you can take the sum or the maximum, I don't know if the maximum makes sense, the sum, you can do something of this type, which makes sense in general.
Yes, I assume. They actually structure the proof differently, I have to say. So I can't guarantee that this works, the proof I gave works in the general case, but I can guarantee that the claim holds in the general case. They quote some Cohen-Hewitt factorization theorem, which I didn't have the time to understand, but it gives the exact same conclusion. So I don't. Yeah, there might be some extra tricks you need to use to make it work in the non-commutative case. I don't know, but okay. Right. So we could take an example of this theorem, a non-commutative example. So we could take A, which I kind of mentioned earlier, A to be bounded operators on a Hilbert space, and then I to be the ideal of compact operators. And in this case, we get a category. So D A to B, for which the continuous K theory of this D A to B is this topological K theory KU. This is a rephrasing of this theorem of Karoubi, Suslin-Wodzicki. Sorry, who's the other name I mentioned him yesterday? The homotopy invariance guy, Higson. Yeah. So okay, well, so now we know. Right, this in some sense answers a question I asked in the beginning of the first lecture. So I was talking about this result that the K theory of the ring of compact operators is a non-unital ring is topological KU, and I asked where is the category? Well, here's the category, but it's not quite satisfactory because it's how do you actually understand this category? Like, well, how do you think of an object in this category, and so on and so forth? What structure does this category have? So we will get back to that. But first I want to make a small algebraic digression, so which will help motivate this. Algebraic analog, which in some sense we've already seen, but in another sense we haven't. So let R be let's say a commutative ring. And let's take A to be the ring of, so, sorry, huh?
What is Higson's role? I mean, isn't this already, just...
Oh, I thought the homotopy invariance statement was, the homotopy invariance of algebraic K theory was proved by Higson following an argument of Kasparov, but yeah.
Okay.
Yeah. No, for algebraic. But I mean, not in general, obviously, but once you have compact once you tensor in some completed sense with compact operators. So, yeah. Okay, let's look at an algebraic analog. So endomorphisms of some countably infinite direct sum of copies of R, endomorphisms as an R module, so just some infinite matrix ring, and then I equals the finite rank endomorphisms. And finite rank just means, say, that it's a map from this guy to itself that factors through a finite direct sum. Instead of, okay, so let's ask the more baby question. How can we think of the category given by the kernel in this case? Well, what is dA? Well, kind of by Morita theory, you should think of So this is endomorphisms of some object in some category. So the small subcategory that's generated by that is just the fixed subcategory generated by this thing. So you take this object in R modules, and you close it up under cones and sums and shifts and so on, and retracts. And then you take ind of that. That's one way of understanding. So this is inside D of R. So you're kind of taking a new generator of D of R that's not compact, and you're kind of formally declaring it to be compact, is one way of understanding this. But then actually, so what I'm going to claim is that, so D of A to B in this case is just dr. And the way to see it is to say, okay, well, we have a functor from dr into here, and in fact we have a localization situation because if we've included, because actually already inside this stage we have all of perf R. Simply because R is a retract of the infinite direct sum of copies of R. So if so perf R is including here on the level of compact objects, so we get the start of what should be a localization sequence from the full derived category of R to D of A. And then you can ask what is the left adjoint, and the claim is the left adjoint. It sends the infinite direct sum of copies of R to the in system, which is the in system of the finite direct sums of copies of R. So. And from this you can see, well, formally we know that the quotient category, which is whatever it is, category X, we know it's compactly generated by the image of this compact generator. And with this formula for the left adjoint, you can calculate what the endomorphisms of that object are, and you'll get exactly the quotient of this ring by this ring. So this is actually, it's a version of the very thing we wrote down with the countable, the Culkin category based on Aleph-1 compact objects. So we just didn't use all Aleph-1 compact objects, we just used the free R modules of countable rank, but it's the same kind of story. Okay. But this is kind of how you maybe want to think of the compact of this setting here. So what is this? So the derived category of compact operators. So how to think of it? So take the category. So just additive category of infinite dimensional separable Hilbert spaces. Then take its bounded derived category. So you're just looking at finite chain complexes. So you basically want to pretend that these guys are projective objects, and you're forming a bounded derived category in that sense. And then take ind. So you formally adjoin colimits. So that's what D of bounded operators on any given Hilbert space is. But now we've phrased it in a way where we don't have to fix the Hilbert space for whoever was asking that question earlier. So now it's completely invariant. Okay. And then dk is the full subcategory generated by sequential colimits of the form Hilbert space, etc., along compact transition maps. Full subcategory of this D of bounded operators on H. So you can think that what kind of category has Ku as its algebraic K-theory? Well, it's a category where you formally think of Hilbert spaces as compact projective objects. And then you consider the following types of functional analytic spaces. They're given by filtered colimits like this. You can even assume they're injective if you like. When the transition maps are compact operators, these are a certain class of dual Fréchet spaces, which are not at all exotic if you've studied functional analysis. And that's a dualizable category, and then its algebraic K-theory is topological K-theory. And let me make a remark. This categorical perspective is actually quite useful. Sorry? Oh, well, I claim that this dk is the fiber here. And then I claimed from Wojcicki's theorem that that was an idempotent situation. So the combination of those two facts implies it's dualizable.
By the series term of last time?
No, only by what I've said today. Yeah, but well, I think we might have another explanation for this in a second.
This here is just like the Kalkin category of the above.
Kalkin category? Where? X? Oh, yes. Yeah. Well, it's not literally the same as the Kalkin category I used last time. For the Kalkin category I used last time, you'd have to take all countably generated things here and not just free ones sitting in degree 0. So it could possibly live in all degrees. But yeah, it's a mild variant, a bounded variant. Okay. So yeah. So with this perspective, we can see that this thing, dk, is a commutative algebra object in PRST dual. Via, so, well, this L2 tensor product of Hilbert spaces. So that gives a symmetric monoidal structure on the big category, D of B, and then the fact that compact tensor compact is compact. So a tensor product, an L2 tensor product of two Hilbert space of two compact operators is still a compact operator. That's all you need to know, and you deduce, for reasons we'll get to later, I think that promotes this to that gives a symmetric monoidal structure on this category, which actually promotes it to a commutative algebra object in this category. And that implies that you get a E-infinity ring spectrum structure on this D of K. Well, and of course you should have expected such a thing because it's Ku, and we know Ku is an E-infinity ring. It has all the multiplicative structure. But from the original perspective of K-theory of non-unital rings, I always found this very obscure. And in fact, I think people had to work quite hard to see from the functional analysis perspective this E-infinity ring structure on Ku. But now it just comes from evident categorical structure. So that's one of the nice things about this Efimov theory. And now let me close this small. Oh, I'm not quite close. Let me ask a question. So, an aspirational question. I don't know quite whether the answer should be yes or no, but I really am really hoping that it's yes, or at least some small modification is yes. So in operator algebra theories, there's a famous theory called bivariant K-theory. So there's topological K-theory of C-star algebras, which we've seen is related to algebraic K-theory. And then KK theory is defined for a pair of algebras. And what KK A comma B is supposed to be is it's the kind of thing that gives you natural maps from K theory of A to K theory of B. And it's a category. So my question is, does there exist a category enriched in PR dual stable with objects C-star algebras such that applying continuous K-theory to the mapping spaces gives the usual KK category. So this thing I explained here solves the most basic question, which is KK from C to C, complex numbers to complex numbers. But the question is, can you understand all KK groups in this way? Is the famously difficult and technical Kasparov product on KK groups, which gives the composition law in this KK category and is the main tool in K-theory of operator algebras, does that just come from some categorical structure, similarly to how I explained in the case of the E-infinity ring structure on KU? That's, I think, an interesting question. Okay.
What is this dk equal? Dk is some presentable, is a derived category, okay. You can write it like this. But then Ku is a spectrum. So how can you write equal?
Oh, sorry, I forgot K's. There are too many K's in it. Because K is, yeah, I already saw one K and I thought I was done, but there's the K that's compact operators and then there's the K that's algebraic K-theory. Thank you, Ofer. Yeah. What is? Which, where?
Like, can you give an example of this?
An example of what?
Yeah, this equality.
How do you give an example of an equality?
Oh, I don't
like
know.
you take just you work just like if you have a perpetuate ring.
No, but now I moved to a different context. Now it's real like Archimedean functional analysis. So I left perfectoid rings in the dust.
So you can't talk about Bott elements.
Well, actually, we'll have to make a discussion of Bott elements at some time, but not today. Yeah.
Could I ask you a question about your so special case that so if you have an operator algebra and some K-theory of an operator algebra, does that fit into this? Can that be realized with the K-theory of realizable categories?
Oh, you're talking about the case of like KK from C to your algebra? I think so. I think I can do that. I'm not 100% sure. Yeah, it's more the K homology that's interesting. The other way around. Yeah. Yeah, I think some suitable generalization of this.
So what was the result about algebraic K-theory of something tensor this compact operator?
That's the theorem is that if you take a C-star algebra and you tensor it with, I don't know, minimal tensor product, whatever, with a C-star algebra of compact operators, then the algebraic K-theory of that is the same as its topological K-theory, which is also the same as the topological K-theory of your original C-star algebra. Yeah. So now I'm going to make a remark whose true meaning will maybe only be come to the fore tomorrow, but there's something special happening with bounded operators on a Hilbert space. So any two-sided ideal, not necessarily closed or anything, this is a purely algebraic fact, in bounded operators on a Hilbert space, is flat as a left module. For the same reason, it's a filtered colimit of free modules of rank 1. It's fun to try to prove. I invite you to give it a shot. So to get idempotency, you basically just need I equals I squared. And one choice is compact operators. But it's not, I'm going to try to argue in the next lecture, it's not the best choice. for two reasons. But the best choice, this is, okay, now this is my opinion, okay? The best choice is it's, in literature it's called, I think, S0 plus. So it's called the Schatten ideal of operators. So Schatten ideal. So this is the intersection over all p bigger than 0 of Schatten ideal SP, and this is the p summable operators. So S1 is the trace class operators. S2 is the Hilbert-Schmidt operators. These guys, those kinds, they don't satisfy this because, for example, a composition of two Hilbert-Schmidt things is always trace class. So you compose more, you get more summability, and you can't kind of break it up and go backwards. So these classes get moved amongst themselves when you take I squared. But if you go to the limit in either direction, then you get something that satisfies I equals I squared, and for which you now get a category that you can discuss. This category, the resulting category, will be studied in the next lecture. And I will there give the reasons why it's a better choice than the choice of compact operators.
Sorry, can I ask a question?
Yes.
Isn't the best choice because you're thinking about like the concurrently regulator or something like this?
Yes. That's one way of saying it. Yeah. Or that's one way of saying one of the reasons. Yeah. Mm-hmm.
Can you clarify what best choice means? Well, I mean, like for what purpose?
Yes, I can, and I'll do it at the next lecture.
Oh, okay.
Yeah. Yeah.
What did he say?
He asked if it was related to some Conn-Karoubi regulator, the reason why I call this the best choice. Other questions? Okay. Okay. Just in case you guys aren't sick of functional analysis, but let's move to the non-Archimedean setting so you can pretend it's algebra. So non-Archimedean analog. So let's say R is a commutative Noetherian ring. And let's say it's complete with respect to an ideal. Okay, this is not going to be our A and B. They're not going to be R and R mod I. I already said the Noetherian case is boring. But what I'm going to take is A to be endomorphisms of, you take a direct sum again of countably many copies of R, but then you recomplete it. So now it's a kind of functional analysis object, you could say. And then, yeah, I've got too many I's. I'd say J is those compact operators, let's say, i.e. Those that are finite rank mod I to the n for all n.
So the I complete is out of the endomorphism for I.
What's that?
The I completion is for the endomorphism ring?
No.
No?
Well, not a priori. I mean, I wrote it like this.
Finite rank means finitely generated image.
Sorry?
Finite rank, you mean finitely generated image?
Yes. But it's also the same as it lands in some finite summand of R mod I to the n. Yeah.
It lands in the finite, okay, the component.
Yeah, it's the same as the purely algebraic discussion I had earlier, yeah. I mean, I had a purely algebraic discussion with no ideal, just R, and it's the same notion of finite rank as there, yeah. So it's not so obvious actually why this gives you an idempotent situation, and I won't give the argument right now, but you get a category But you do get a dualizable category. So, and this is the category called nuc R. And it has it has a better interpretation. You can actually think of it as parametrizing certain I-adic functional analytic objects. And again, we'll get to that a bit later. But for now, I just want to state the main result, which is a truly remarkable theorem of Sasha. So first of all, note that, well, whatever this category is, if you reduce mod I to the n, you get the purely algebraic story I had before. And in that case, I argued that the category you get is the usual category of modules over R mod I to the n. So note that there's a functor like this. Not an equivalence, but a functor. And the theorem of Efimov is on the level of K-theory, that's what happens. Yes, I know, but it didn't make sense at the time. I mean, yeah, I mean, he also didn't make it precise, so I mean, I didn't quite know. I didn't want to ask the question and then answer it when I knew I was going to do it later. Okay. So I was going to sketch the proof. I think I'll skip it so that I can get on to other stuff. But maybe I'll say the idea. The idea is you don't use the defining presentation of this category. You come up with a new presentation of this category, which is adapted to calculating the K-theory. So you can write this as you can make it into, so you find a new way of writing this as the kernel of a localization functor between two compactly generated categories. And these ones this one will have K-theory, well, they'll both have K-theory equal to the product of K-theories of R mod I to the n. And the functor will induce the usual kind of shift minus identity transition map on the level of K-theories. And the mechanism by which any category could possibly be equal to a product of K-theories is a slight modification of the amazing fact proved by Gunnar Carlson that K-theory of categories commutes with infinite products. So the cartoon version, which is wrong, is that C is ind of the product of perf R mod I to the n. It's actually a modification of that, and D is also, but that's the cartoon version. And then there's a functor that induces the shift minus the identity map, and there's a localization sequence. That's cartoonish, it's wrong, there are many subtleties. Sasha Efimov overcame them all and proved this remarkable theorem. Okay. So
all the I is a J or I.
Thank you. No, the I's are I's, the J's are J's. I think I got it right.
So J is independent with the choice?
Well, J.
Oh.
I mean.
Okay, yeah, okay.
J depends on, I mean, it doesn't really, I mean, it depends on the closed on the closed subset of spec R cut out by I. I mean, in a sense, it depends on I.
Does Efimov's proof use anything special about K-theory as a localizing invariant?
Yes. I mean, here's maybe I'll state a companion theorem of Adriano Cordova is the same for THH. And basically, you can expect a theorem like this when this is not a mathematical statement, understand. But you can expect a theorem like this if your localizing invariant happens to commute with infinite products.
Thanks.
Yeah. And I think it was not known for THH before Adriano investigated this. But yeah, it's true, according to him. Right. So that was a kind of hands-on look at some examples, but I find this discussion kind of unsatisfactory because I didn't properly explain how to think about these categories as categories. I mean, like, what are the objects, what are the morphisms, and so on. So now we're going to return to to dualizable categories, but from an internal perspective. So we can get a look at what's going on inside these categories. Here's a definition, which in this form I got from Akil. So let C be a presentable stable infinity category. A map f from x to y in C is called compact. So we used to have compact objects, and now the big punchline is going to be compact objects are good for thinking about dualizable categories, but compact maps are good for thinking, compact objects are good for thinking about compactly generated categories, but compact maps are good for thinking about dualizable categories. So what's the definition? If whenever you have a filtered system, or co-filtered, I don't know, Zi with colimit 0. Okay, if you have a random colimit, just pass to the fibers of the things and you'll get something 0. So this is quite a general situation. Then for all maps from y to Zi, so for all maps y to Zi, there exists a j bigger than I such that x goes to y, goes to Zi, goes to Zj. This is null homotopic. Okay. Let me make some orienting remarks, which you should take as exercises. So if for x in C, the identity map from x to itself is a compact map, if and only if x is a compact object. So compact maps forms a two-sided ideal in the sense that if you have a compact map and you compose it on either side with an arbitrary map, it's still compact. And 3 is if C is compactly generated, then f from x to y is a compact map if and only if it factors through a compact object. Okay?
Definition, co-filtered. So co-filtered, you mean like for every two objects there's something that maps to both? Or
no, they both map to it. So it's growing, not shrinking. Yeah. So it's the same concept that you use to define a compact object. It's yeah. I don't know if you're supposed to say filtered or co-filtered. So yeah. Filtered?
I think it's filtered.
Oh God. Oh, shit, okay. Yeah, of course. Right. Okay, so, and here's a proposition giving the internal characterization. So for C in PRL, the following are equivalent. And the first is that C is dualizable. And the second is, well, I'll give two conditions, 2 and 3, and they're both ways of expressing that C is generated by compact maps. just in the same way as a compactly generated category is generated by compact objects. So the first way of phrasing that is saying that C is generated under colimits by objects of the form sequential colimit of some system where these transition maps are all compact. And the third condition would be that is a combination of two conditions, A and B. A says every compact map is a composition of two compact maps. That's an interesting property that's always satisfied in a dualizable category. It's reminiscent of this I equals I squared thing. And the second part of the condition is that if Z in C is such that for all compact maps X to Z, we have F is null homotopic, then Z equals 0.
Sorry, could you repeat the second condition for any Z such that for any what?
Oh, so if Z is an object which satisfies the following condition, then Z is 0. Now what's the condition? You took the words right out of my mouth. The condition is that any compact map with target Z is null homotopic. So what is the key to this? So for general, any object, any sequential colimit along compact maps is, well, Aleph1 compact, but moreover, so let's say, well, any sequential system, any sequential in system with compact transition maps, so x0, x1, etc., then Homs from the colimit of this system to an arbitrary filtered colimit. This is an arbitrary filtered colimit, is the same as Homs in the in category. So this is what the compact maps kind of give you at a more precise level. So this is like a condition about a null homotopy, but this is a condition about two mapping spaces agreeing. And this and this also explains why C dualizable implies C Aleph1 compactly generated. In fact, the Aleph1 compact objects are exactly the collection of these colimits along compact operators. And it also shows that my description of the D of K using Hilbert spaces in compact maps was not an accident, and it was not actually artificial. if you're going to describe a dualizable category, it has to be able to be described in this form, in precisely that form.
I have a very non-well-posed question.
Yes.
May I ask you?
Thanks for warning.
Yeah, so just as in this Bodziski result, can we somehow expect that there is a notion of abstract, I don't know, stable ideals or something like that, which would be this, which the compact morphism in a stable infinity category would be an example of, and have some description, some independent sort of description.
Yeah, so I defined what a compact map is, but there's a more precise notion of what Johnston and Joyal called a wavy arrow. So a compact map makes sense in any thing in PRL, but the wavy arrow only makes sense in the dualizable case, and it means that when you apply this left adjoint to the onate embedding, it factors through a compact object there. So it's like, yeah. But then you can give a witness for that factoring, and you can define a whole anima of wavy arrows or a spectrum of wavy arrows. Whereas this is just a condition on a set of maps. And so certainly that thing is well behaved, although it's so structured that it's kind of hard to get a hold of. And I'm telling you the best I can say about these compact maps currently. So yeah.
So here is Aleph1 filter colimit?
No. No, it's the opposite thing. It's a countable colimit. So this would be like a finite colimit. If Aleph1 were Aleph0, then this would be like a finite colimit. So it wouldn't be filtered. Yeah. It's a countable colimit. So if these were all compact objects, then this countable colimit would be Aleph1 compact. Meaning Homs to any Aleph1 filtered thing, you could pull it in. They go really high up, so that's why I had to jump those Aleph1 filtered. Yeah, and so that's kind of a hint. That tells you why this is true in the compactly generated case. I mean, because I said there that each of these maps factors through a compact object, so then you'd be getting an equivalent in system of just compact objects, and you'd see that it behaves like an ind object, and that that the resulting colimit is Aleph1 compact. But the claim is it's completely general. You don't need to have compact objects to make that argument. It's enough for the maps to be compact.
So number 2 of this proposition, so yeah. It implies that like if you have a dualizable category, there's a lot of compact objects?
No, it implies there's a lot of compact maps.
These maps are compact?
Yes. Yes. Yeah, it's the maps that are compact. We decidedly do not have enough compact objects in a general dualizable category. Okay, so my time is up. I'll just quickly say what I will get to next time. Next time I'm going to, in some sense, continue this discussion. I'll explain how this idea of compact maps lets you build a machine lets you produce many more examples of dualizable categories. In particular, I'll explain this dualizable inverse limits and dualizable internal Hom. And then I'm not going to have much time, but I'll get to analytic spaces in the non-Archimedean and the Archimedean setting. Maybe just the non-Archimedean setting, after all. But thank you for your attention.
More questions?
Yes. So you said for a T-star algebra, you have a way of producing a category whose algebraic or Efimov K-theory is the topological K-theory.
Well, I said I think. I mean, I don't know. Yeah.
So the question is, do you have a way of doing this for Blanc topological K-theory?
No, I think that's a different kind of thing. I don't. No, I certainly don't. Certainly don't. Well, I'm going to give a reason in the Archimedean context why it's very hard to avoid having negative K groups. And semi-topological K theory doesn't have any negative K groups. Yes.
I just, maybe you explained it, but I didn't quite get. So, you started the lecture, well, previous lecture, with this fact that K-theory of compact operators is equivalent to the topological K-theory.
Yes. I didn't prove it.
Oh, but does this perspective kind of help to give a different proof? Or?
I think so. I think so, but I can't actually give you a proof. It helps with some of the steps, for sure. But not the full proof. I don't see how it helps with the full. I mean, the key for me, the key of the proof is this magic homotopy invariance, which is some crazy argument that I don't even understand. That kind of goes back to Kasparov, and but some of the surrounding structure of the proof, which in my opinion is not the key, but some of that is facilitated by using this language instead.
But so in particular for this, it's not still true that it's kind of like you can see those level of categories.
Sorry?
No, one of the motivation you started that like you want to see as many properties of K-theory on the level of category.
That's right. This homotopy invariance is something I do not know how to see. Oh, wait. No, I don't know how to see it on the level of category. Yeah. It's a very, very interesting question. Yeah. Yes?
In the same setting for the derived category bounded operators, is there something internal to that category where you should feel that your K-theory will have periodicity?
Yes. Well, if you believe homotopy invariance, yes. So one thing I'll explain, it was another remarkable insight of Karoubi's. It's related to some of the previous answers I just gave, is that in things like this K-theory of K, you can explicitly write down what's supposed to be the inverse to the Bott element. And I'll explain a very clever construction of this. Well, I probably won't get to it. Talk to me on Thursday or Friday if I don't get to it. But there's a very clever construction of this. And the inverse to the Bott element is, from a classical perspective, the hard thing. I mean, it's easy to produce the Bott element in algebraic topology, but only because it's homotopy invariant. Like, the source of the Bott element is that K1, secretly, is that K1 of the complex numbers is C cross, but then it's homotopified, so it turns into S1, and that pops up to a Z in the next degree. And that's the Bott class. And so if you have the inverse Bott, and you have homotopy invariance, then Bott periodicity is immediate. So really the key to everything is homotopy invariance. And I don't know how to see that homotopy invariance from this perspective, but at least you get a very, very clean construction of this, whereas Karoubi's construction is a bit crazy. You have to write down explicit formulas on a torus with sines and cosines and so on. I'll give you a very good reason why it exists. But again, I want to emphasize the key thing is homotopy invariance, and I don't know how to do that I don't know how to do it at all. I don't understand their arguments. So, yeah. Yeah.
Yes? Just out of curiosity, does this perspective, like intrinsic perspective on generalizable categories, help you say something about invertible categories, or invertible objects there?
Oh, I wish.
Okay.
That's a big mystery to me, this question of whether, for example, every invertible category is compactly generated.
Exactly, yes.
Yeah, sorry, I got nothing to say about it. Yeah.
Yes? So in the case of compact operators on a conceptual infinite dimensional Hilbert space, what is the unit? Like you claimed there's a commutative algebra.
Yeah. So the unit, so in the category I was discussing here, you have your separable Hilbert spaces. There are projectors in them that give you a rank 1 summand, a one-dimensional copy of the complex numbers. That's the unit. So I could have said, I said you start with the category of separable infinite dimensional Hilbert spaces. I could have left out infinite dimensional. I would have gotten the same category in the end because of retracts. Yeah. And I should have said it like that so that the unit was obvious.
Yeah. Okay, so when one works with things like almost ring theory, so the existence of compact generator given by finitely generated projectives fails because you have only up to almost.
Yeah.
So are those categories, like derived categories for almost rings, Do they enter in your formalism?
Yes, yes, they're exactly dualizable, but not compactly generated. Yeah, yeah, exactly. And I claim that these are the good replacements for your compact generators.
So is there a direct description of the D of I, the non-unital ring thing?
Well, yeah, I guess you could say it's kind of I guess you could say it's non-unital I modules satisfying a certain condition, namely that I tensor I am isomorphically to M. You think it's obvious, but that's only because you're used to unital rings. So yeah, I think the category D of I is just that you look at non-unital modules satisfying this condition here. Yeah, you can just trace through what you get by looking at the unitalization.
So which assumption on I? So I first of all is a non-unital ring spectrum.
It's an H-unital non-unital ring spectrum.
So you need this I tensor I equal to I to start off the.
Yeah.
Otherwise it doesn't. Okay. And you said that if you work with things like just chain complexes, like you can do I tensor I over a base. Because to define I tensor I, in some sense you have to embed I in a it's really tensoring over a unital ring in which I is a two-sided ideal. But there are many choices of this because you can use either a sphere spectrum or HZ or some base combinative ring, and in the case of this probability, all the choices are give the.
Yes.
Yes.
But did you define it in terms of, bar resolution, but some semi-simplification?
Yeah, that's right. I was implicitly working in base category spectra.
Okay, but so if you take the bar resolution over Z or over a base ring, then it gives you the same condition.
Well, yes.
If one is holds, the other holds.
That's correct. Yes, at least in the connective case. Yeah. I mean, one implication always, and then the reverse, at least in the connective case. That's the extent of what I could glean from Georg's article. I hope I'm not misinterpreting anything.
From which article? From?
Excision in Algebraic K-theory revisited. Right? Yeah.
Okay, let's thank Dustin here.